Mm. Good evening, everyone. So, today we'll be discussing the doubts and problems that has been covered in week 8 lectures. So, welcome to the NPTEL course of Carbon Materials and Manufacturing of week 8 where we will discuss some problems, concepts, and we'll see some questions numerical and some theoretical questions that will be helpful to solve your assignments. So my name is Saurabh Soni, and let's begin with the today's class. Yeah, so our first question is our first question is cross sectional is given. It is numerical. Cross sectional area of five individual carbon fibers are given, which is 100, 80, 50, 30, and 90 micro meter square. The test filament prepared using these fibers fails at 5 Newton. Okay, so they have given that it fails at 5 Newton. So we have to calculate that the value of ultimate tensile strength, which is UTS, and Young's modulus of the material. Take true compliance as 0.05 mm per Newton, gauge length as 20 mm, and magnification factor of the micrographs as 200. So here they have given. So firstly, you have to identify that what is what question is saying and what you have to find out. Okay. So okay. So in this question, as you can see here, they have given some values. So firstly, you need to understand. So they have given the cross sectional areas. Okay, of carbon fibers. So cross sectional area is given. So you have to write here, given that is cross sectional area. So cross sectional area, it means AF. AF is how much they have given? 100, 80, 50, 30, 90 micrometer square respectively. Okay, so this is they have given. Now it is saying the test filament prepare using this fiber fails at 5 Newton. So what does that mean? What is this? Force is 5 Newton. Now they have given now you have to okay, they have also given the true compliance as 0.05 mm per Newton. So how you represent this? C equals to 0.05 mm per Newton. Now the gauge length is how much? 20 mm. So let's say L is gauge length and it is how much? 20 mm. Now the magnification factor of micrographs is represented by 200 mf and it is given 200. Okay. So what you have to find out is the UTS. Okay. What you have to find out is UTS, ultimate tensile strength. This, and the second one is your Young's modulus of the material. This. So this is okay. So this is given in the questions, and this you need to find out. So can anybody guess or try to solve this? Then we will discuss that how it will process if you won't get. Or I have given you the hint, and you need to then solve it. It is very simple. So firstly, I want you guys to solve by yourself, and then I'll if you can't, then I'll show you that how it can be solved. So did anybody solved it completely? If not, then let me solve this for you. Or if you will have any doubt in further, then you can drop a message in the comment box. And so this is very simple. So as you can see here, the first thing is given here is the carbon cross sectional area for the carbon fibers, which is represented by AF, and the force where it I mean it fails, which is 5 Newton, and the compliance is 0.05, and the gauge length is 20 mm, and the micro magnification factor for the micrograph is 20. You have to find this UTS first, and the second is your Young's second thing is your Young's modulus. Okay, so let me write this is if for the simplification, you first thing is your UTS. Okay, so UTS is how much? UTS is given by F by A. So here, how much F is given? 5, where it fails. And what is the value of A? Okay, so you have to find out the value of A. So how you will find the value of A? So the what is A? A is nothing but your average filament area. Okay, so average filament area is given by A, and A equals to summation of AF multiplied by 10 is to power 6, sorry, 10 is to power minus 6 multiplied by 10 is to power minus 6, and this will come in mm square. Okay, because it is given in the micrometer square. So when you have to convert mm, then you have to multiply this and divided by this is F and multiplied by 200, which is your magnification factor. So this will come in m square. So when you calculate this, then it will be coming around 1.75 into 10 is to power minus 9 millimeter square. So this is the value of your A. Okay, now what you have to do here, this value will go here. So here in UTS you have to put the value of A, which is equals to 1.75 into 10 is to power minus 9. Okay, so when you divide, so how much it will come, your UTS value will be around 2.86 into 10 is to power 9. Okay, so you can convert this to better it, you can write it in the GPA. So it will be 2.8686 GPA. So this is the value of your UTS. So this is your answer first. Now you have to calculate answer number 2. So answer 2 is very simple. So in 2 you have to find out the Young's modulus. So Young's modulus formula is very simple. You have to divide L upon C multiplied by A. So value of L is given, which is 20 in the given that, and the C is your, which is compliance 0.05, and the value of A we just find out 1.75 into 10 is to power minus 9. So the value of E, when you calculate, it will come around 228 0.57 or 58 somewhere. Sorry, it is also, you have to convert it in the GPa. Okay, so this is like, okay, so yeah, so this is your answer number 2. So this is how, again I will try to explain this one more time for the sake of your easiness. The question is given, the cross sectional area of the carbon fibers, individual carbon fibers, which is around 100, 80, 50, 30, 90 micrometer square. So here you have to, the filament fails at 5 Newton, and you have to calculate the UTS and the Young's modulus. And here the compliance is 0.05 and the gauge length is 20 mm and the magnification factor is given. Okay, now the UTS formula is F by A. So A, how you have to find is average filament area, the summation of AF. So AF is different. So AF is like 100, 80, 50, 30, 90. So here you have to do the summation. Okay, so and you have to convert into mm square. So it will come 1.75 into 10 is to power minus 9 mm square. Okay, then you put the value that in this way you can find out the UTS, which is coming around 2.86 GPa. Now for the Young's modulus, the formula is again simple, L by Ca. So you have to put the value of L, you have to put the value of C and the A, which we have calculated. So it will be coming somewhere around 228.58 GPa. So in this way we can solve. So this is just a simple formula based. The only tricky part is you have to take the average filament area. You have to calculate, which is given individually. So which is also not a very difficult task. So probably in your assignments, if you will have this kind of a questions, then you can be able to solve this. Okay, uh, now, okay, so in our previous lectures we have gone in our previous lectures we have learned many things about this kind of technique, where we have fabricating our carbon fibers by using electrospinning and different methods. So here we'll see a little bit about the electrospinning again. So in this way, the distance between the electrodes is 10 to 12 centimeters traditionally. It can be varied depending upon whether you are using a short and a long length, and the setup can be horizontal or vertical, both. I mean, for an example, okay, for an example, your one electrode can be sorry, your one electrode can be here and your substrate can be here. So it is like a horizontal. Okay, and it could be like your one electrode here and your substrate could be here. So it is like a vertically. Okay, so it is possible in both the directions. And the case of vertical setup, there is less fiber wastage. So when you will be using this vertical setup, so there will be a it is saying that there will be a less wastage will be there in this particular case. Now the horizontal setup enables removal of droplets and very thin fibers as they fall down due to gravity. Okay, because of here will be gravity, then it is enables to remove the removal of the droplets and the thin fibers. Now the collectors can be rotating. So here, as you can see, your collector, which is another electrode, it can be this kind of whether it could be a this flat shape, or it could be like this drum shape, or it could be like this disc which will be rotating. So here you can see, here it is a horizontal. I mean, from one electrode will be here needle, and from here your fiber is coming and it is getting collected somewhere here. And here it is your one electrode is here, from where your fiber is coming, and it is in the vertical direction, it is collected in this collector. Similarly, you can use this kind of a drum. So this drum will be continuously rotating. So all over the drum you will get fiber. And similarly, this is a disk also, so here you will get your fiber in the disk. So this is continuously keep on in rotation, so it is continuously moving. So for collectors can be rotating. So what you will get when it will be rotating, so you will suppose if it is not rotating, then you will only get a collection of your fiber somewhere near, which is continuously exposing to the collector. But if it is rotating, then you will get a uniformly collection of your fibers throughout the drum. So this is the main reason of rotation. And the lab scale electrospinners can be constructed in house. Collectors must be grounded. Okay, so the collectors, it means to say this things must be grounded. I mean, electrically it should be grounded, and the safety precaution must be taken during the experiment. Humidity and the temperature is one of the most important factor. So in the spinning chamber, that can be very important, and closed PMMA chamber is preferred in this case. Now the industrial electrospinners are a multi-nozzle system for large area electrospinning. If the spun polymer is electrically conducting, okay, for an example, your polymer is conductive, fiber connection between the two electrodes may lead to a current flow. Okay, if it is conductive, then there is chances of your flow of your current. Okay, now the high current flow through the fiber can cause a spark or fiber burning. Yeah, so suppose if it is a very highly conductive, then there is a chances of a high current flow. Okay, so due to that, there is a chances of your burning or sparking Okay, now the electrically conductivity of polymer may not play a very significant role on spinability of a polymer, but it is a known to affect the uniformity of fibers. Okay, so this will be helpful for that. So these are some factors that you need to focus upon the electro spinning part. Okay, so this is the electro spinning. So I think till here we have explained many concepts related to electro spinning. So if you have any doubt regarding this, then you can ask now. I can again try to solve this, or I can answer your questions. So the next concept that we'll be uh, going to cover is our stabilization of polyacrylonitrile. Okay, so here in this you can see this is your pan, and this is your dehydrogenation. So here what is happening, as you can see, so this is your pan. Okay, so in dehydrogenation you will get reduce of oxygen and H2O. So here one extra bond will come. Now it will go for the cyclization. Okay, and then oxidization. So here it is a little bit of chemistry. You have to know that how this bonds formation is happening, and how this is forming after carbonizations. Okay, so since this polymer comes in a form of powder which is mixed with a solvent, most common dimethyl formamide or formaldehyde, which is nothing but a DMF, in various concentration varying from 5 to 15%. Fibers are generally electrospun at 10 to 12 kilovolt, and fibers mate is stabilized at 240 to 350 degrees centigrade for at least 1 hour. Okay, in air for stabilization, and then carbonized under the inert atmosphere. So this is the reaction. So I'm also not very expert in this reactions, but you can watch the lecture, or you can understand better that there are many videos which will explain you the stabilization of your polyacrylonitrile, which is nothing but a pen. So yeah, so this is very good concept, that how this carbonization of polyacrylonitrile, which is pan, is happening. So the stabilization is diffusion control process for which the temperature is increases required. Okay, so it is saying that in the diffusion, so wherever this process diffusion is happening, so you have to control the temperature. Okay, you have to control the temperature. Now however, we can't increase the temperature too much, else it will damage the fibers. Okay, so you have to somewhere optimize the temperature so that the diffusion can happen, but at the same time you have to optimize in such a way that it should not go to a very high temperature. Very high temperature it should not go, otherwise your carbon fiber, okay, your carbon fiber will burn out, right? So that will become ash. So this you have to think. The challenge is ensure the release of byproducts without creating pores or mechanically damaging fibers. Yeah, so wherever you are playing with the temperature, so there is a challenge. Okay, so what is that challenge? So challenge is nothing but uh, I mean ensure the release of byproducts without creating pores. Okay, so if you will applying here temperature, then there is a chances of creation of a pores. So it should not form. Pores should not form. At the same time, pores should not form. At the same time, it should not be mechanically damaged. Okay, it should not damage or burn. A gradual heat treatment for longer duration is preferred, and stabilized fibers are converted into carbon under the inert atmosphere at temperature more than 900 degree centigrade. So this is the temperature where the stabilized fibers are converted into carbon. Okay, so here you have to use a inert atmosphere such as your nitrogen or argon, about 900 degree centigrade for the stabilization. Pyrolysis mechanism of pan-derived carbon can be understood by measuring the properties of the intermediate materials. Okay, so here you can analyze through this. Now the pan carbon intermediate materials are prepared at different temperature points during the pyrolysis of pan fibers. Now, by observing the properties of these materials, mechanism of pyrolysis can be understood when you will analyze the property. So property of any material after carbonization is very important to analyze. The electrical mechanical properties of the material drastically changes drastically around 700 degree centigrade. Okay, so this you have to take care that how much temperature you are using and what property you want. So the electrical and mechanical property changes drastically when you will reach around 700 degree centigrade. This indicates the loss of most heteroatoms and formation of carbon networks at this temperature. Okay, so usually there is a suppose this is your carbon fibers, and in between you will have some lot of atoms. So when you will expose to the high temperature, when you will expose to the high temperature, then this some random atoms and heteroatoms that can be removed. Okay, and only your carbon fibers networks will form at this temperature. So in this image you can see this is a pen fiber mat, which is how beautifully it has formed by electrospinning. So yeah, this is like that. And this is stabilized pen fiber mat, and this is carbonized. So this is stabilized and this is carbonized pen fiber mat. So that's why it is looking grayish or black in color. And this is a magnified image of your pan derived carbon fiber mat. So yeah, this is how you can carbonize the pan. Is there any question of on this slide? If you have any questions, then you can ask, then we will move to the next slide. Okay, now, so here the carbonization of polyacrylonitrile. Uh, so in this you can see how it is happening. So the ultra thin, if you want a ultra thin, less than 20 nanometer fibers may feature a high graphitic content at temperature as low as 900 degrees centigrade. So low temperature pan derived carbon fibers are not graphitic, but it had, so if you will use a low temperature, okay, then it is not graphitic, okay, but when you use a higher temperature it may show some graphitization. Okay, so you have very well known from my previous lectures that what is non-graphitization, what is graphitization. If not, then you can watch the previous lectures. And one can use additives such as carbon nanotubes to further enhance graphitization. So CNT is a material that can enhance your graphitization. And yeah, and also also for industrial graphitic carbon fibers, mesoporous pitch is preferred as a precursor. So here you can see electrous pan CNT pan fibers after carbonization at 900 degrees centigrade. So this is a, you can see a zoomed image how beautifully it has carbonized. And yeah, so the electrical properties of pan carbon intermediate. So here you can see, so here your resistance is which is in the mega ohm around 60-70. Your and pyrolysis when you will do, then as I have mentioned in the previous slide, that after 500 600 the electrical property started change. Why? Because suppose there is a some hetero atoms in between the carbon fibers, but when you expose to the high temperature, it's got removal. Okay, it gets removal. Now only the carbon fibers will remain. So carbon is a conductive material. Okay, so here the slowly your conductivity is increasing, that means the resistance is decreasing. But after a certain around 700 degree, so let's say it is a 700 degree centigrade, your electrical property is completely changed and your resistance will decrease and it will become a very highly conductive. Okay, why? Because the atoms or some atoms could be there, and that is probably act as an insulator. So at a very high temperature, so here you can see at a very higher temperature there is a removal of heteroatoms. Heteroatoms. So due to this, it will be your conductivity will increase and your resistance will drastically decrease. So this is the reason. Okay. So after this, mechanical. Okay, so like as you can see, the electrical property of the material has drastically changed. So there are mechanical properties. You have to see whether how the electrical property is changing and how the mechanical property is changing. Okay, so here the mechanical property. So what could be there in the mechanical property, as we have solved the questions in our, so let's say you can take UTS, you can take Young's modulus and the yield strength of the material, Young modulus. So these are the different mechanical properties of the material that you have to concern about that. So the mechanical strength test carbon fiber. So the UTS, the Young modulus, are usually determined using ASTM. The full form for the ASTM is American Society for Testing and Materials. So standard on Universal Testing Machine, UTM. So if you have seen the UTM machine, then you probably know that we can do all this testing. Okay, and if not, then you can go in the YouTube or some go just Google out that what is UTM machine. You can see that where you can do all kind of a testing. So the tensile test can be performed on a single fiber strand or a bundle of fibers. Okay, test can be performed single fiber or here we can take a single fiber or we can take a bundle of fibers. Okay, here you will have a lot of fibers. Now single fiber test is time consuming, may not be realistic if fibers are not uniform. Okay, so it should be like a very uniform, otherwise it won't give a good results. Testing fiber bundle pose difficulty to align all fibers along the direction of the load applied. Okay, it's saying that the testing fiber bundles pose difficulty to align all the fibers, okay, along the one direction of the load applied. Suppose you have applied the load in this direction, then it is very difficult to align this all the in the one direction. Friction between fibers and twisting of fibers. Okay, now the prepared specimen loaded on machine, how you have to do. So there is a machine, so there will be a one clamp this side and then another clamp is this side, so you have to load your machine in between. Okay, axis of the fiber along align with the axis of the cross head of the uniform stress distribution. Suppose if you want to do the tensile, then you have to fix so there are a different kind of holders or the sample holders where you can do your testing and apply load. Okay, whether you want to do a tensile or whether you want to so in tensile test you have to apply a force in opposite direction. In compression you have to apply the force in the direction opposite. Okay, and then the fiber stretched, you have to stretch this fiber. Suppose here your length is continuously increasing, so at certain point of time your fibers, let's say after this point, it will break. Okay, so it will break like this, so you have to stretch this fiber in such a way that it will gets break, and from there you can test all the you can analyze all the properties. Okay, so here you will have a paper tab. This is glue or wax, and this is your gauge length, and this is your fiber, and this is your gripping area. Okay, so you have to then apply a force in this direction. Okay, so after this process, this process, as we have discussed in our first slide, the Young modulus, the formula for Young modulus is the L upon C into A. So what is L? L is nothing but is your gauge length. And what is C? C is your true compliance. And A is your average cross-sectional area of the specimen. Okay. So this C is calculated by CS minus CA. So CS is what? System compliance. CA is indicated compliance. How you calculate this CA? I into S by F into S. So what is I? I is full scale elongation. H is your cross head speed. S is your charge speed. And F is your full scale load. So here UTS is calculated. UTS is calculated by your F, which is failure load, divided by the area. So the load at which your materials fail, and area is the area of your material. So here you can see, for an example, this is a plot. So we are increase. So I will explain this here. So this is your load. Okay. So here here we are continuously increasing the load, and the displacement is increasing. Okay, so here let's say like this. Sorry. Yeah, so here it will be like this, and at some point there will be your yield point. If you have known the stress strain curve, so this is your displacement. So here you will apply some preload, and then you will increase the load, and this is your yield point. So you have to apply load like this, and you will get a displacement. So after indicated compliance, here specimen length. Okay, so specimen length will also increase. So typical load displacement curve for carbon fiber specimen is somewhere look like this, and this is your compliant specimen length. So here this is your stress strain curve. From here you can get. So you have to know, for an example, this axis is your stress, and this axis is your strain. Okay, so if your material is brittle, then it will be fail like this. So this is your brittle material. But your material is ductile, then here it will go like this, and you will get some yield point here, and this will be your UTS. Somewhere here you will get a UTS, and here your material will get fracture, and here you will get a yield point, and this is for the ductile material. Okay, and this is for the brittle material. So this is your ductile and stress strain curve for carbon fibers. How it will look? It will be like this. It will go like this, and it will get fracture here. Okay, so this is your so this point corresponding to this fracture point is nothing but your tensile strength, and this is your strength, this is your stress. So sigma y is so here in this diagram you can see this is your yield strength. So yield strength is this, corresponding to this, and UTS is this. So for brittle and for ductile this. And how we to calculate this yield strength, and this is calculated by Hooke's law. This is your E into strain. E is your Young modulus, and this is your strain. So measure of so what is Young modulus? Young modulus is nothing but the measure of stiffness of your material, that how stiff your material is. Now, the stretching fibers, when you stress the fiber at high temperature, aligns the change along the fiber axis, and the stiff and tensile strength of the fiber is increased. Okay, so when you will stress the fiber, let's suppose at very high temperature, not very high temperature, but yeah, relatively high temperature. So that will align the chain along the fiber axis, and your Young modulus. Okay, this Young modulus E is your Young modulus and your tensile strength. Okay, this. So when you will do it high temperature, so that will increase, so that will goes up. So depending on precursor, carbon fiber can be turbostratic or graphitic. Okay, turbostratic means. So the turbostratic means pan based carbon fiber. Graphitic mesophase pitch based carbon fiber. Turbostatic carbon fibers have high value of tensile strength, and the graphitic carbon fibers have the higher Young modulus. So that's mean when you will use a turbostatic carbon fiber, it means like a pan based, then it will give you a just a second. If you will use a turbostatic carbon fiber, then it will have a UTS value will be the higher. But if you will use a graphitic carbon based fiber, then it will have a high Young modulus. Okay, so high Young modulus, it means that it is a higher stiffness. It is very high, and the material will have a high stiffness. Okay, so that's the reason. So I hope it is clear. If not, then you can ask questions or try to solve some numerical related to the basic stress strain concepts, and that will be easy. That will help to solve your in fact assignment problem. So in the cross sectional area of the fiber bundle, okay, so how you have to so here you can see this is a TM image. The scale size is 5 nanometer, so you can see how this is the SM image of carbon fiber and this is the TM image. So this is in the 400 and this is when you will further magnify this, so this will look like this. So this is very beautiful image of carbon fiber. So the optical microscopes of magnification 200 is used to capture the image of individual fibers, single fiber, a number of individual fibers, or you can say the bundle of fibers. So you can use 200 x optical microscopes, and area may be calculated using a planimeter from the micrographs, and you can use for the area calculation you can use this formula, and in this formula it is your area can be calculated as summation of AF and into in the first questions numerical we have done this calculation into 10 is to power minus 6 and into MF chi square. So n is nothing but the number of fibers under the observation, okay, and here the MF is a photomicrograph magnification factor and AF is your area of the one fiber in mm square. So by using this formula, you can calculate your area. Now the diameter measurement for single fiber can also be done using SCM. Okay. So suppose this is your SCM image. So diameter measurement, what is the diameter of this fiber? Can also be done using SCM. Laser micrometer is another equipment for the diameter. So like SCM, you will have a laser micrometer. So these are for the calculating the diameters, and the various image processing tools are available. Softwares are also available which enable counting fibers in a bundle, void measurements between two fibers. Suppose there is a void, and what is the void between two fibers you can also calculate, and the TM can be used for observing the microstructures. Okay, so yeah, here you can see this is your TEM image, and this is your SCM image. So yeah, these are some my imaging techniques that you can see to observe the carbon fibers. So this is again the same questions which just to recap the formula which I have just shown. So here you can see the cross sectional area is given and the force failure is given, and here you have to calculate the UTS and the Young modulus. So in the previous we have just shown few minutes ago that you have to calculate this A, and you have to apply the formula of UTS and the Young's modulus, and then you can calculate both. Okay, so now here the advanced carbon fiber fabrication via electrospinning. So we have need this electrospinning enough that how it's done and what are its process and how we use electrodes and collectors in order to get fibers. Now the application of carbon fibers are primarily determined okay, so determined, okay, so in any material, especially in the carbon based or the carbon fibers material, the which I have already said, the first thing is your mechanical property, okay, and the second thing is your electrical property. So you have to, yeah, so you have to show your you have to check your mechanical property, you have to check your electrical property, and there are some surface properties are just such as your surface area and your surface functional group. Okay, so these are also some things that you have to determine. So mechanical strength of carbon fiber is limited by their crystallinity and present of defects and flaws. So suppose like in the stress strain curve, if you are some heteroatoms, or you can say some defects and flaw will be there, then your mechanical property can vary. But if you will have a very pure carbon fibers, then you might get a very different value for your um, materials, such as your UTS, ultimate tensile strength, or your yield strength, or the Young's modulus. Now the crystallinity can be controlled. Okay, so crystallinity, yeah, can be controlled by using a right precursor. Okay, so first thing should be your precursor. Precursor should be your right. Okay, so on the basis of your precursors, the whole process is depends at how much temperature you have to do for the carbonization, or for the different process. Okay, and the heat treatment conditions. Okay, so heat treatment condition is, I have already spent the how much, temperature you are applying at what temperature your other atoms which are unwantedly present in your material, that can be removed by using a heat treatment conditions. Okay, so that will provide you the crystallinity in your material. Now the presence of flaws can be calculated using a method proposed by Reynolds and Sharp. Now if the fiber diameter are small, there is a less possibilities of flaws. Okay, so if that C, suppose your diameter is very less, then there is a less possibilities of the flaws. Okay, here, but your diameter is a high, then it can be a probability that here you can have some defects and the flaws. Now the precursor modification during carbon fiber fabrication. So the fabrication of low density hollow fiber. Okay, so how it will done? The coaxial electrospinning using a low carbon containing polymers as core and a high carbon polymer as cell, mixing various nanoparticles into the polymers to carbonization. So here you have to mix the polymer into your nanoparticles for the carbonizations. Okay, now the surface activation using physical and the chemical method. So here you can see the macro and the micro defects in the carbon fiber. So this is your defects, this is your defects. So yeah, if you will have a thicker, then you will probably be getting ending as a high flaws are the defective kind of a material, but you will have a thin, then a less probability of presence of your defects. Now the carbon fiber decorated with nanoparticles. Here you can see how when you will be using the nanoparticles. So these are your nanoparticles. So this is arranged like this. So these are your carbon fibers where you have, coated, you can say, or you can say the mixed or decorated with the nanoparticles. So this is just like a schematic representation, but yeah, this is true. And here you can see, yeah, so here you can see in the top images, hollow carbon fiber prepared by PMMA core, pan shell followed by carbonization. So this is your PMMA, core is PMMA, and the pan shell is your pan, and this is followed by your carbonizations. So yeah. Now, so when you will have a pan derived carbon fiber, so here this is your tensile strength versus your temperature. So here you can see when you will be increasing the temperature. Okay, let me take a pen. Yeah. So here you can see in the when you will do the experiment. So when you increase the temperature, so here your temperature is increasing, and so your tensile strength is also okay. So here you can see this is your tensile strength. Okay. So it's some till some point, let's say suppose here till 1500 centigrade your tensile strength is increasing, but after a certain time if you will expose to the very high temperature here, if you will expose to the very high temperature, then it starts burning out and your mechanical properties starting losing. Okay. So tensile strength, here you can see what is tensile strength. So it is a maximum stress material can handle. Okay, so after the further temperature your tensile strength starts to decrease. And here if you will see the Young's modulus, so Young's modulus of your material, the Young's modulus is nothing but it will show that how stiff your material is. So here when you will do the stress strain diagram, so the slope of this curve is given by your Young's modulus. Okay, so here you can see it is continuously increasing, and after some point of time it will starts like a saturating situation when you will increase the temperature. So this is your plot for the tensile strength and the Young's modulus for the pan derived carbon fiber. Okay, so here let's say your carbon fiber, sorry, critical flaw size. So your critical flaw size is given by the alpha. So let's say you will have okay, so let's say you will have this carbon fiber, and you will have flaw in between. Okay, so flaw, then you will carbon fiber will be like this. Okay, so this is your flaw. Now as you all know, the if you will have some defects of flaw, that it will affect the property of your material or the carbon fibers. So it is very important to know that the critical flaw size, or the what is the flaw size present in the material. So it is given by some formula which is nothing but the 2 into E into gamma A divided by pi into sigma f square. Okay, so here E is what? Young's modulus. This is your surface energy of the graphite. So usually how much we take this? So 2.2 joule per meter square for your graphite, and this is your tensile strength of a single fiber, you can say. So in your assignments you can get a questions for this. So here you just need to put the value of your tensile strength and your Young's modulus, and then you probably so here like in the questions I have seen that the value of which you were getting was around 170. So here you can put 170 into surface energy 4.2 divided by pi into 4.2 square. Okay, so here your 1 will cut down, and what you will be end up getting is 2 into 170 divided by pi into 4.2. Yeah, so probably in your assignments you will be having this kind of a question. So here let me just show you the question. So hope you have known this question. So this is the question. Yeah, so this is the question, the calculate. Okay, so let me draw this question here, so that yeah, so here it is giving you this question. So this question is asking about this. So what it is asking, to calculate the size of the largest possible defect if the tensile strength of the fiber is 4.2. So here you have to write in this question, you have to write in this question that tensile strength. Okay, so tensile strength is given. So how much it is given? It is 4.2 GPa. And Young's modulus is how much? 170 GPa. And the surface energy gamma is given 4.2 joule per meter square. Now you have to find the flaw size. Okay, so critical flaw size is given by the alpha. And what is the formula? Formula for this is the 2 into E into surface energy divided by pi into your tensile strength, square of your tensile strength. So when you will put the value 2 into your E 170 and into your 4.2, this is your 2, and now pi into 4.2 square. So it is cut and it will be coming around 20, sorry, it will be coming around 25.8 somewhere. So this is, I think, in micrometer. So this will be your flaw size. So yeah, so this is the answer for this question you can have. Okay. Hmm. So now how can you use this carbon fibers in your day-to-day life? I mean, what are the important applications of using your carbon fibers and where can we use it? Okay, so the large scale manufacturing applications carbon fibers in the form of carbon fiber reinforced polymer. Okay, so you can't, I mean, you can use, but in most of the cases you have to mix this carbon fiber with your polymer. Okay, so what it will become? It will become a carbon fiber reinforced polymer. Okay, so you have to reinforce the polymer so that you can make it suitable for the many applications. Now the carbon fibers are directly used at a small scale such as electronic and the sensor devices. So you can use this for many sensing applications because it is a conductive, and you can use it for the electronic purpose, and use of thin carbon fiber means for culture of biological cells and tissues. Okay, so since it is a biocompatible property, I think that's why we can use this carbon fiber mat, or you can say this carbon fiber for the culturing of your cells. You can grow the cells on top of this. And now the biosensor fabrication using carbon fiber mats decorated with nanoparticles or other nanomaterials. Biosensor fabrication using carbon fiber tips can also be done, and you can sense some bioactivity. And micro device fabrication using single carbon fibers, integration of electrospinning with other microfabrication techniques such as lithography. You can I mean, you can use a lithography in order to fabricate microfabrication techniques. And flexible micro device such as your neural sensor fabrication by patterning carbon fiber mats also you can do. So here you can see for the neurals, it sends the brain activity in your neural sensing. So here you will have some this kind of a design. So this will be your patch and it will come like this, and at last it will be connected to here. Okay, so this will go inside your neural. Um, so on so in order to get the signals from your brain, so in this way you can use this for getting some signals from your brain like EEG, or you can monitor your many things. You can sense like a sleep monitoring device. And ligament implants, for that you can also use this composites, researchers are using. And the membrane filtration using activated carbon filter. So here you can see this is a micro pattern carbon fiber for the neural sensing. Also here it will be go inside, and this is a carbon fiber bundle in a glass capillary for biosensing. Okay, so these are some good applications that where you can use your micro your carbon fibers as a micro device or as a neural sensors. Okay, so yeah, these are some areas where you can do your research, or you can further investigate if you want to do use your carbon fibers as a uh, uh, carbon fiber for the good applications. Okay, so now the machining. Okay, so machining, how we'll do this carbon fiber reinforced plastics or the polymers, how will we do the machining part? So the machining carbon fibers reinforced plastic. So here the I mean this carbon fiber and laminates require, after fabrication you requires a cutting, milling, drilling, and many machining processes for meeting the required tolerance and also for the fitting and the joining. Now the drilling and milling cause delamination, that is the layer of the laminate separates from each other. Okay, so here you will have a let's say you will have a different layer. So when you will do the drilling or the milling, the layers separate from the of the laminate separate from each other. Now the delamination may accompany fiber breakage and splitting. Okay, when you will do the tensile, then there is a breakage of the fiber. When you will apply the compressive, then it could be split. Okay, so it can break into the two parts. Now the top and bottom layers uh, feature more severe defects as they are only supported on one side. It has been observed that the increased feed path tooth increases the delamination factor. Okay, so here you can see this is milling for the edges. In this diagram, you can see so how beautifully it has, removing this. This is milling, and it will go like this. Now, the reason is the material is anisotropic and non-uniform. It varies scale. You can say the microstructure or the bulk or the fiber level, and the polymer causes some damping, and it's not thermally conductive. Okay, while carbon fibers are conductive, carbon fiber can contain of different composite may also vary, and that will lead to a different mechanism during the machining. So here you can see the first one is your peel up delimitation here, and this is your push down. Okay, now this is your top view of drilling damage, how it is drilling. Now the what is the uh, machining of this reinforced plastic, what is the advancement and what are the solutions? So machining parts using a laser beam. So what is the advantage if you will use a laser beam? Then your advantage will be it will be residue free, and it will be easy to operate, okay, and fast. The disadvantage will be your heat affected zone may damage the edge. So yeah, and if you will do a water jet, if you will do the water jet, a jet of water constantly accompanies the tool. So you will continuously having a high force of water, and that will accompanies the tool. So advantage is your they reduce the thermal. Okay, so you won't get your materials should won't get heated so much. So there is a reduction in the thermal and the mechanical stress in your tool, and that will be continuously removal of your chips, and it will give you a high flexibility as well as the will increase the sharpness of your tool. The disadvantage is your water needs to be, microfilter, so that any uh, contamination cannot come during your process. And also after the process, this water should be treated, because it is not well for the further use. We can't let it go like as before. Now, if you will do the carbon dioxide, which is nothing but a dry ice blasting, so a jet of dry ice is blasted onto the surface for constant cleaning and cooling while machining. So what is the advantage of this CO2 blasting is dry and residue free process it is, and the low hardness of the disadvantage is you will get a low hardness of CO2 particles compared to the other blasting approaches. Combination of these two techniques is also used, where you can use a water jet cutting and the CO2 blasting. There are some other techniques which you can use for the machining of your carbon fiber reinforced plastics, where you can use a flexible super abrasive belts integrated with robot for kinematic guiding, abrasive diamond silicon carbide coated tool and milling tool for the improvement of milling processes. Use of ceramic tools can also be used for the lower thermal wear. So here you can see that here it is a edge milling, using a laser beam. So this is your laser beam. So the laser beam is coming here, and this is your drilling. Okay, so inside you will drill, and this is your edge milling. So you are just cutting out the edge. So what is the advanced finishing techniques is the edge routing, drill grinding using abrasive grinding point, and the dry face grinding with the alumina grinding. So these are some machining techniques by using which you can thin down your materials, and you can make it whatever the shape you want for the further application. Now the carbon based composite, so there is composite material. So the material is composed of two or more physically and chemically distinct space, so which is a composite, which we call composite. Okay, so one of them is binder. Okay, so the first one is your binder, which we matrix, and the other is additive. Okay, so there will be matrix and the another one which we add. So these phases can be in the form of different materials or the same materials but different forms, example carbon or the carbon composite. Additives is also called the reinforcement. So there you will have a two parts. What are those two parts? So first one is your matrix and the another one is your reinforcement, and this is called the composites. Now the carbon or the resins composite use carbon structure used as additive, and resin as a matrix, and the carbon fiber are mostly commonly used carbon structure for composite preparation. Carbon nanotubes and carries carbon are also used as a reinforcement. Fiber may be short or woven fiber, like short fibers are mixed into the polymer in a random fashion. In the second type, mats are oriented layer by layer. Here you can say some laminate, and the resin infused between them. They are known as the laminates. Carbon laminates. Carbon fiber based composites are known as the carbon fiber reinforced polymer or the plastic. Examples of the other similar composite materials: glass fiber reinforced plastics, also commonly known as fiberglass. So here you can see the carbon fibers. This is adding, and this is your resins. So here this is as a result you will get, and this is the laminates of your carbon fabric composite. So you will get a layer by layer, okay, of your fiber and your resins. So yeah, we will see some few concepts and the numerical related to today's lecture. And if you will have some doubt, then please let me know. So yeah, thank you all.